So what you're going to do is you're going to have your flip book right here. Is it showing? Okay, perfect. You're going to have your flip book right here, and we are going to graph some rational functions. Now, let's go back a couple of days. What makes a rational function? By definition, when you hear the word rational, you know you're dealing with a what?
Real number.
True, but what types of numbers are written as rationals? I said it over here on the flip book. Remember right here? I said rationals are fractions. So this entire page, we were simplifying, add, subtract, multiply, dividing, or solving fractional functions or equations. Now we are graphing fractional functions. Okay, so we've done a lot of this with our naked graphs and our shifts, and we'll talk about how that relates to this a little bit today. It looks harder than it is. It's not that bad, especially today because we're just sticking to the basics today. So we'll just start let's just start with number 4. Okay, so we're just going to start at it. It's nothing else to say, but just start it. Let me get my little book and try to get this showing at the same time.
Is it fractional or fractional?
Either one. All right, so number 1, the first thing you do is factor. Okay, so let's look at number 4. Is there anything I can factor out of 3 or x plus 2? No. So move on. Reduce if possible. Does anything reduce? Nope, move on. Continue past this point using the reduced form. Okay, so the reduced form is just 3 over x plus 2. There's nothing I can do. Now, you'll see today on the next problem that sometimes something reduces. And if it reduces, you got a whole nother ball game. But if it doesn't reduce, just move on. Determine the intercepts, and there's 2 of them. The x-intercept. Okay, now think about this. We've talked about this. The x-intercept, okay, would be right here. What does y have to equal if you have an x-intercept? 0. Okay, so for the x-intercept, y must equal 0. Let me think about it. All right, so y must equal 0 for the x-intercept. So what we're going to do is we're going to set the numerator equal to 0 and solve. The numerator is going to give us our x-intercept. We're going to set the numerator equal to 0 and solve. Our numerator tells us where it crosses the x-axis. The y-intercept, now think about this because we've done this quite a bit. The y-intercept falls on the y-axis. And what is x for any point that's ever existed on the y-axis? Right. So x must equal 0 if it's the y-intercept. So all you have to do is plug 0 in for x in reduced form. That says reduced form. I don't think my pen is going to work very well today. So to get the y-intercept, you plug 0 into reduced form. Now, this is no different than when we got the y-intercept for a linear equation. It's the same thing. So let's get the x and the y-intercepts. Now, let me say this. This one does not have a hole. You can put none or not applicable right there. We will have a hole, I think, in probably the next one, but definitely something that we do today. But it doesn't have a hole. A hole occurs if something cancels and nothing cancels, so we don't have to worry about that today. All right, so to get the x-intercepts, y must be 0. So we're going to set the numerator equal to 0 and solve. Because if the top is 0, the whole thing is 0. 0 over any number is 0. So what we're going to do, now watch this. We're going to set the top equal to 0. Now, we've learned this. Does 3 equal 0? No, that is not true. 3 does not equal 0. There's no variable there. I can't solve for anything. So if that happens and you just have a number on the top, there is no x-intercept. Put none. You'll see why in just a minute. All right, to get the y-intercept, you plug a 0 into reduced form. So here's reduced form. So to get the y-intercept, we just plug in a 0. 0 plus 2, that's 3 over 2. We want to convert these to decimals because it's easier to graph. So that's going to be 1.5. Now, remember that the y-intercept is an ordered pair. So put 0, 1.5. There's the y-intercept. Okay, we start talking about something called an asymptote after this. An asymptote, we've already looked at asymptotes, you just didn't know that that was the word for them. An asymptote is a line that the graph can never cross. It approaches it and it gets really close, but it never ever crosses it, okay? So we have used these before when we were drawing our naked graphs and our shifts. We used asymptotes. We just didn't call them that word. So don't go get overwhelmed by this next little section. Determine the asymptotes. Okay, number one are vertical asymptotes. Those are asymptotes that go like this vertically. This is easy. We've already done this. You can never cross a vertical asymptote. Okay, that's number one. Step two, oh, I forgot. You need to write down what a vertical asymptote is. Why do I not have this written down? A vertical asymptote is the restrictions on the domain. Now, we've already had a test on this, so that's going to be really easy. We'll do that next because it's super easy. So a vertical asymptote is the restrictions on the domain. I do not know why. I thought I had this typed in, but obviously not. You have to fill in the blank a little bit. We've already had a test on this. We know that you cannot have what in the denominator? Well, it can't equal 0, right? You can't have 0 in the denominator. X plus 2 cannot equal 0. So therefore, x cannot equal -2. Oops, forgot my negative. This is what we call a vertical asymptote. So on the VA line, put x cannot equal -2. That is not hard. We've already had a test on that. Now the next one, we're not going to do, there's a third type of asymptote called an oblique asymptote. We're not going to do that today. So we're just going to do horizontal and vertical today. We're going to stick with the easy stuff. Then we'll do obliques on Thursday probably. But if you have a horizontal asymptote, you have two choices. If it's bottom heavy, which I'm going to talk about what that means, the asymptote is y equals 0. If it's top heavy, it is this is so important. It's the top coefficient over the bottom coefficient. Now, what does it mean to be bottom heavy or equal degree? And top heavy we'll talk about on Thursday. But bottom heavy means there's more x's on the bottom than there are on the top. When I say x's, I mean the exponent, the power of x's. And equal degree means there's the same power of x's on the top as there is the power of x's on the bottom. So, for example, if you have an x squared on top and an x squared on the bottom, it's equal degree. If you have an x cubed on the top and an x cubed on the bottom, it's equal degree. But if you have more on the bottom, maybe you have an x squared on the bottom and an x1 on the top, then it's bottom heavy. And again, this will come on Thursday. Thursday. So let's look at the one that we have. Where are there more x's, top, bottom, or equal? Bottom, okay? There's one x on the bottom, and there are no x's on the top. So this is what we call top heavy. So if it is top heavy, you got to read your, I'm sorry, not top heavy, bottom heavy. What am I thinking? B-O-T-T-O-M. It's bottom heavy. I'm sorry, my fault. Because there's more x's on the bottom than there are on the top. If it is bottom heavy, you don't have to do any work. The asymptote is just at y equals 0. And that's it. We're Garrett graph it. That's all you need. That stuff right there.
Bottom heavy. Y equals 0.
Yes.
Every time.
Every time. If there's more x's on the bottom. Now, what you're looking at is the exponents. So having one x is bottom heavy compared to having no x's on the top. Now, you can look at number 5 and see, is this top heavy, bottom heavy, or equal degree? No.
There's a x squared and a top x.
No. You're looking at, this has an x squared and this has an x squared. So these are the same. This is equal degree, number 5. These will be equal degree. But this one is bottom heavy because the exponent on the bottom, which is 1, is more than the exponent on the top because there is no exponent on the top. So it's bottom heavy. Now, all we have to do is plot that stuff. There is not one thing on this that we have not already learned. We've already learned x-intercepts, y-intercepts. We've actually learned asymptotes. We just didn't call them that. We knew that you could not have a 0 in the denominator. We knew that x could not equal 2. So we already knew all this. We're just putting it together. So very carefully, let's start graphing it up. Okay, we don't have a hole. I'll show you what a hole is in just a minute. We don't have an x-intercept. Now, what that tells me is it does not cross the x-axis. So when I start drawing this little thing in just a minute, it can't cross the x-axis. Okay, it does not have an x-intercept, so it cannot cross the x-axis. All right, the y-intercept is at 0 and 1.5. So go over 0, up 1.5, and put yourself a dot. We have a vertical asymptote at -2. Remember your lines, Vernox and Hoy. This is a vertical line. Now, you want to make it a dotted line because it's not part of your graph. It's just going to tell you we're going to get some shape out of it.
Wait, where do we put that one?
-2. X cannot equal -2. So go to -2 on the x-axis because the line is x cannot be -2. Go to -2, make a vertical line. Now, it does not cross the x-axis, so I'm going to put little tick marks all along the x-axis, telling myself, you can't cross the red line. So I've got two asymptotes. I have a horizontal asymptote, and I have a vertical asymptote. It cannot cross those red lines. I don't know if y'all can see that red very well, but those are your two asymptotes. All right, are we good up to that point in time? Okay, so my own daughter is doing this. She's taking Math 171 online, and the other day she started kind of getting bogged down in this because this, I mean, her teacher taught it a little bit different, but this can feel like a lot. And I was like, hold, stop, just test a point. You don't have to memorize a bunch of rules. You don't have to memorize 1 and 3, 2 and 4, shift left, rotate around the x-axis, flipped over the y-axis, stretch, compress. Hold, stop. You're thinking too much. Let's just test a point. Now, we don't have to test a point over here because I already know what the graph's going to do. So you can connect this with a slide. It has to hit that point, but it can't cross the red lines. I already know that because I had a point. All you need is 1 point. 1 point is enough. But what I do not know is if this is, let me show you what I don't know. I'm going to give y'all a model with this paper clip. I don't know if the other part of the graph is in quadrant, what we're going to call 2. In other words, is this going to look like a volcano? Try to straighten out this paper clip. All right, so my question is it going to be there or is it going to be there? And you don't want to have to memorize a whole bunch of stuff because I'm here to show you it's just much easier to test a point. So we just need to figure out, is it going to be a volcano shape or is it going to be a 1 and 3? So I need to test a point. I need to test 1 point over here. I don't have to test a point there because I already know where it went. We have never in our lives seen anything that did this. We've never seen anything that did like that. Not in this class. So that's not an option. I had that 1 point, so that takes care of that side. But I have no idea what's going on over here. I don't know if it's going to be up there, like a volcano, or down here. So let's just pick a point. All right, Nathan, give me 1 point to the left of my hand. Negative 5? Okay, so he wants to test negative 5. So what you're going to do is you're going to test negative 5, and that's what Nathan just told me to test. He could have said negative 3. He could have said negative 4. He could have said negative 8. He could have said negative 10, but he said negative 5. So what I do is I go to my formula, which is 3 over x plus 2, and I test it. So if I put in a negative 5, I'm going to get negative 5 plus 2, which is negative 3, which is negative 1. So my test point will be at negative 5, negative 1. When in doubt, test a point and see where the point is. That's the best way to do this, is to test a point. If you don't trust yourself, you can test 2 points and make sure that they fall in the same quadrant. But based on what Nathan told me, he picked negative 5. He probably did that strategically, but we're not sure. Plug the negative 5 in. So I've got 3 over negative 5 plus 2. Negative 5 plus 2 is negative 3. Positive 3 divided by negative 3 is negative 1. So this is what we call our test point. So plot that point. All right, so we're going to go to the left 5 and down 1. 1, 2, 3, 4, 5. Oh, wow, I cannot see it. Hold on, let me start over. 1, 2, 3, 4, 5, and then down 1. There we go. So based on that test point that Nathan just gave us, is this going to be a volcano? No. Is this going to be a 1 and 3? Yeah. Yeah. Gonna be a 1. Because when I plotted that point, it was down here. So my graph has to fall down here because that's where my test point was. If my test point had ended up here, then it would have been a volcano. And we'll see one today that does. All right, let me slide that over. I want you to look at that. I want you to like, take a deep breath on that. It's pretty basic. It does get harder. All right. Let's share contacts. Let's try number 5. Let me think about number 5. I think it's going to be pretty hard, but that's okay. Let's do number 5. All right, slide it up. Let's do number 5. Now, I'm getting my little paper. We talked about our rules. We need our rules to work for us. We need our notes to work for us, not us to work for our notes. So I've got my notes. I must have zoomed out because I'm not able to show it. All right, number 1, factor. So we got to be good at factoring in order to get these rational equations. What does x squared minus 9 factor to? Good, x plus 3, x minus 3. And then we're going to factor this. What will multiply together to give us a positive 6 and add together to give us a negative 5. That would be an x minus 2 and an x minus 3. All right, now this one's going to be harder, so get ready. All right, let's look at our rules. Number 1, factor. I just did that. Number 2, well, this is still part of number 1. Reduce if possible. We already learned how to reduce. Remember this? This was on this page right here. Factor, state the restrictions, and cancel identical factors top and bottom. So we now know, because this is a rational function, that we can cancel identical factors on the top and bottom. So what's going to cancel? X minus 3. Now, if something if something cancels, you have what's called a hole, an actual hole in the graph. And I'm going to show you this. I might pull it up. Well, yeah, I'm going to show you this on Desmos.com. You have an actual hole at x minus 3. Now, this is the hardest part. So let's read our paper. If a term cancels, which it did, you have a hole in the graph. So you got a hole in this graph. When I say hole, I mean like an open circle. I mean an actual hole in the graph, and I'll try to show it to you today. You have to find the hole, which is an x, y coordinate. It's not hard, but you do have to pay attention. All right, so a hole occurs at x minus 3. And if we set that equal to 0, we get x equals 3. That is where the hole occurs. It occurs wherever x equals 3. Now, let's go ahead and write the reduced form. Reduced form, because those are going to cancel, is x plus 3 on top and x minus 2 on the bottom. That is reduced form. Write that down. And we know that a hole occurs at that missing point. Let me try to explain to you what just happened. We started with a function. We started with a rational expression, a rational graph. That something just canceled. It was there a few minutes ago, and now we just wiped it out. So we have to mathematically hold that position and let people know, hey, there used to be something there, but we took it away. We took away an x minus 3 from this original problem. And when we take away an x minus 3, it's going to leave a hole at x minus 3. Now, you got to find the y coordinate of the hole. The hole is an xy coordinate. So we know that x is 3 because that's where the hole occurred. Where do you think you're going to plug in to get the y coordinate? No, we know the hole is at 3. We just got to find out what y is at 3. So where are we going to plug that 3 in? Yeah, right here for reduced form. So plug this in. We've got 3 plus 3 over 3 minus 2. 3 plus 3 is 6. 3 minus 2 is 1. And so the hole occurs at 3, 6. We just found out where the hole is. And I mean a literal hole in the graph. I will show you this on Desmos.com in just a minute. I'm not exactly sure how Collaborate works with me switching over from the live screen to internet, but we'll see. I'll put it in and see what happens. All right, so we know that a hole occurs at the coordinate 3, 6. Go back. Here's how I got 3. I said, all right, if this is going to cancel, I have to find the value of that hole. And so I solved x minus 3 equals 0, and I got x equals 3. I plug 3 into reduced form because once you get reduced form, everything else comes from reduced form. You don't ever look back at that original problem. All right, let's get our x-intercepts. Now read the paper. Set the numerator equal to 0 and solve. So again, once you get reduced form, you're always looking back at this. You don't go back to the original. So the numerator is x plus 3. So we're going to set that equal and we're going to solve. And so my x-intercept is at negative 3 comma 0. We're going to finish this problem. I'm going to show you this problem on on Desmos.com, and then we're going to take a break, come back and do some more.
Hold on, so x.
You get the x-intercept by setting the numerator equal to 0 and solving. So you take your numerator, which was x plus 3, you set it equal to 0, and you solve. That gives you your x-intercept. Now, you got to put it in an ordered pair, which we've talked about this. There's a difference in a line. This is a line. This is an ordered pair. An x-intercept is an ordered pair that goes through the x-axis. All right, look at your notes. To get the y-intercept, we're going to plug a 0 into reduced form. So go to reduced form because you always go back to reduced form. It's x plus 3 over x minus 2, and we're going to plug a 0 in to get our y-intercept. It's going to be 3 over negative 2, which is negative 1.5. So my y-intercept is 0, negative 1.5. All right, my paper got cut off a little bit. but it looks like I had VA right here and then HA down there. We're going to do it in that order. You got to be careful though, because some worksheets switch it up and put HA and then VA. All right, so vertical asymptotes. You have a vertical asymptote occurs where you have a restriction in the domain. We have studied this a bazillion times. So if you go to reduced form, all right, what can x minus 2, well, let's come down here. What can x minus 2 not equal? 0, and therefore x cannot equal 2. So this is a vertical asymptote. X cannot equal positive 2. Now, some people, and I understand because I'm very particular about notation, so I understand this question, but they say, well, what if we put x equals 2? That's fine. There is a vertical asymptote where x equals 2 because for this problem, x cannot equal 2. Let me say that again. There is a vertical asymptote where x equals 2 because for this problem right here, x cannot equal 2 because 2 minus 2 is 0. Did you have a question?
How does 0 minus 2 equal -1?
Did I do that wrong? Yes, I did. The answer is -1.5. I'm sorry. Thank you. That's a correction, Kayla. Fix that. It is still -1.5. I guess I jumped ahead of myself. See what she's saying? I had miscalculated there. 0 minus 2 is -2, and 3 divided by -2 is -1.5. Thank you. I had jumped ahead to the answer, I guess, in my mind. And then the last thing we have to do is the horizontal asymptotes. Now, for today, we just have two choices, bottom heavy or equal degree. On Thursday, we'll do top heavy, and that is a whole different game. But for today, bottom heavy or equal degree. Now, when I say degree, the degree is the exponent. So this one has an x squared, and this one has an x squared. So that's what we consider equal degree. It's a quadratic in the top, and it's a quadratic in the bottom. So these are what we say are equal degree. There's not more x's. Now, somebody said something about the fact that this was a 5x down there. That's true, but these are both quadratic equations, so they are equal degree. So if, and this gets confusing, it's easy for this one, but if they are equal degree, you take the top coefficient. Now, what is the coefficient for both of those things? It's 1, right? 1 is the coefficient. So you're going to have 1 over 1, which is 1. This is your horizontal asymptote at y equals 1. It's not 0 this time. 0 occurs when it is bottom heavy. If they are of equal degree, you take the top coefficient divided by the bottom coefficient. And we're getting ready to practice this, so I just want to do these two. I want to show you on Desmos, and then we're going to practice. But we got to graph it. Some people will do all that work. There's one of these on the final exam. You don't want to do all that work and not graph it. I mean, come on, you're just plotting a couple points. So the first thing we do is go to 3, 6, and put an actual hole. So go over 3, up 6, and draw a hole. So 1, 2, 3, 1, 2, 3, 4, 5, 6, and put an actual open circle there because there's a hole at 3, 6.
What's the new finger in the bottom? Okay, I got you.
All right, next we're going to plot our x-intercept. It's at -3, 0. So go over 3, 1, 2, 3. We will plot our y-intercept, which is at 0, 1.5, so it's about right there. And then we have two asymptotes. We have an asymptote at +2. Now remember, asymptotes are not your answer. These are lines that the graph cannot cross, and they give you direction and shape. You approach an asymptote, and you get as close as you ever can to the asymptote without crossing it. So go to 2 on the x and make yourself a kind of like a hashtag so that you know it can't cross that. Oh, this is so good. These are the best 2 examples. I love this stuff. And then it also can't cross at 1. So I go to 1 and I do the same thing. I make a hashtag until it cannot cross the red line.
You said at -1?
Positive 1.
Positive 1?
Y cannot equal positive 1. Oh, something's not right.
I don't know.
Something's not right. I made a mistake somewhere. Does anybody see it?
The wire or something?
Yes, thank you, Tom. I graphed the y-intercept wrong. Let me write that out. Thank you. I knew I made a mistake as soon as I looked at it because I was in 3 quadrants, and we've never had a graph that went in 3 different quadrants, so I had to do something wrong, and Tom has corrected me. Better late than never. So Tom's right. This should have been 0 and then down 1.5. I went 0 and up 1.5. Gosh, I hate to white that out, but I'm going to have to. All right, so it should have been 0 and then down 1.5. I'm going to zoom out on this just because we need to talk about the graph and why you do not need to test a point for this one. All right, let's go to Colin. I'm telling you, Colin, you do not have to test a point for this one. It's not necessary. We had to do it in example 4, but we do not have to test a point here. You can if you want to. Like right then, I knew something was wrong, so I could have tested a point to try to figure out where I went wrong. But why do I not need to test a point? Now think about this little shape I had, Colin. I had this little shape. Oh, well, you know, there it is, the little shape. Why do I not need to test a point for this one, but I did the previous one?
Because you have a hole in the first quadrant.
Uh-huh. I already know, right? What is it doing in quadrant 1? It's going through that hole. What is it doing in quadrant 3? Going through those points. I already know. I already have points there. I don't have to test a point because I already have the points. So literally, like he just said, get as close as you can, then pick your pencil up and come out of the hole, and then you're going to hug the asymptote. Get as close to the red line as you possibly can without crossing it. These are not right angles. I had one person, not in this class, but I had one person on my other class that made them 90 degrees. And I had said it a bazillion times. They are not 90 degrees. They are slides. And so same thing here. Hug the red line, and then swoosh down. You got to hit the points, though. That was the point in doing the math, is to know which points it hits. Now, let me zoom out, and let's look at what we just did, because for today, that's as hard as it's going to get today. We're going to practice this some more. We're getting ready to take a break, and then we're going to practice this some more. But for today, that's as hard as that's going to get. This one had a hole, and we had to find the hole. The first one, we had to test a point. Now, what I want to show you, and like I said, I don't know what my collaborate session is going to do. That's not what I want. I know that's not what I want to do. Stop. Okay. So I like to use, I hope this is showing up, Desmos.com. This is my graphing app preference. I don't want to sign up. Just let me graph something for free, please. There we go, graphing. All right, so you go over here and you type in, I'm going to put number 5 in. So it was x, oh, I'm not good. X squared minus 9. Notice I'm putting in parentheses. Now that's important. Divided by, and then parentheses, x, oh, not that. It's supposed to be parentheses, x squared minus 5x plus 6. Okay, so I'm putting in the graph that we just did. Y'all following me? Tracking me? All right, so let's look at what Desmos.com says and what our paper says. Desmos says it crosses the x-axis at -3. Is this true? See right here where it said it crossed the x-axis at -3? Is that where we had it crossing? Yeah. All right, it says it's going to cross the y-axis. This is, look at your spacing. This is 1, and that's 2. So this is -1.5. That's true. We had that. All right. In general, it said it was kind of going to be a 1 and 3. We agree with that. It looks like, now they don't draw the asymptotes for you on Desmos.com, but you can kind of look at it. It looks like to me that it's never going to cross 2. I can't get my mouse to go. Here's 2. Looks like it's going to approach 2. Let's zoom out. Looks like it's going to approach 2. This would be 2, 4, 6. So it's going to approach 2 forever. Now, the last thing I want to show you is we said that this graph had a hole. And right now, you can't see it. Even if I zoom in, you don't see it. Do y'all see a hole? I don't see a hole. But watch this. We said the hole was at 3, 6. If I trace this, watch when it gets to, you got to watch it because sometimes I can't hold my hand on it. Oh, I just missed it. Wait, here we go. What do you notice happened to the graph? It went to a what? Hole. And it says it's undefined. At 3, and what is that y coordinate right there? 6. See, I have a heart. There we go, 3, 6. The hole is at 3, 6. This is not magic. This is mathematical facts. There is a hole, and sometimes if you zoom in really, really, there we go. Undefined at 3, 6. This is 6. See how it's 6 right here? 3, 6. There is a hole. Okay.